Good afternoon, and thank you very much to our session 2 participants. That was a very spirited discussion and very impassioned. So thank you very much. We all learned a bunch. We now come to our third session this afternoon, and it's I think something that'll be very important to our practitioner community here, and it's a review of statistical and machine learning ideas and methodologies that promise to impact the practice of systematic investing. And we're really fortunate today to have an outstanding roster of professors that have a particular focus in this discipline. Starting out, we have Emmanuel Condas, and Emmanuel comes to us today from Stanford University, where he is a professor of mathematics and statistics and the Barnum-Simons Chair. We thank you for being today. Also with us is Jun Liu, excuse me. Jun comes to us from Harvard University, where he's a professor of statistics. And also with us today is Panos Toulis, excuse me. Panos comes to us from the University of Chicago Booth School of Business, where he is an assistant professor of statistics. I appreciate all of you joining us today. Very excited for this panel. And Ed, I'll turn it over to you. Thank you.
Thank you, John. I would also like to thank our distinguished presenters here on behalf of the Statistical Science Department at Temple University. Thank you for being here, everyone. So like John mentioned, this session is going to be focused on ideas and tools for systematic investing. And we have roughly, a third of our participants from the industry sector and a two-thirds from the academic community. So for people who may not be familiar with systematic investing, the signal-to-noise ratio in this situation is typically very low, even lower than in computational advertising and AdWord type auctions. So methods to tighten the error bars are typically of interest, and especially new ideas that are somewhat model-free, because it's always easy to tighten the error bar assuming a model, but that's typically a fatal mistake in a lot of applications. This is the topic of today's panel. Variable selection independent of interactions, multiple testing, methods that could navigate bias, variance trade-offs, penalize estimations. So we'll explore some new ideas in this space. So in our content library, we have a list of papers by the speakers and also related papers. Recently, Emmanuel Candes put forward the idea of knockoffs. And you can read about knockoff filters on the page that's linked. And in June, even more recently, has been further innovating by introducing a techniques based on data splitting that is leveraging some of these ideas. So I'm going to turn it over to June. June, go ahead. Thank you for being here today.
Thank you very much. Thank you, John, and thank you, Edo, for the nice introduction. It's a great pleasure to be in this panel. So this work is some of our recent progresses. It's completely inspired and also stimulated by the work of Emmanuel Candes, who I guess has moved on somewhat, but a lot of his followers are still working on this related problems. That's very interesting, and also another aspect that motivated us was exactly as Edo mentioned. We try to be more model-free in some sense, but it's always their price to pay. Anyway, okay, so I will, next slide, please. This is collaboration with a few of my students, and I will introduce the FDR control stuff, assuming many of you may not be familiar with the topic. And then I will mostly focus on data splitting ideas. It's actually pretty straightforward in terms of the approach. It just split the data and then do things to create independent confirmations of each other. Okay, next slide. So one of the fundamental concepts of this FDR control was introduced by this landmark paper by Benjamin Hochberg, who are thinking about scenarios where you have many independent hypothesis testing tasks to do. It's just one setting. There are actually many related settings in bioinformatics, in finance, and so on. Basically, you can regard all, there are many different evidences, different so-called signal-like observations, but you want to really discern which one is true signal, which one are noise. So you can formulate them as a p-value problem or the hypothesis testing to test whether the means are non-zero or zero. So the one of the most celebrated or simplified version is the normal means problem. You have a sequence of independent normal observations and with potentially different means and different from zeros, and you want to figure out which one is not zero. So typically you can use p-values and the next slides. And their procedure is to, next slide, please. Is to actually order the p-values and then draw a line which is controlled by the so-called FDR rate. Suppose you want to control the error rate at 10%, 0.1. Then after you order these p-values, you just draw this red line which is touching the other side at 0.1. And then whatever hypothesis p-values under this line will be selected. And you can prove that the false positives below this line, for your selection is somewhat controlled at the level. So this can be proved by when this independent, but when they are correlated, there are some price you have to pay. And if they're not too correlated, this is almost correct. So but if they're too correlated, there could be trouble. There's some relaxations. Next slides. Next slides. Oops. Yeah, so here we are thinking about the situations where there could be correlations. That is, we are thinking about regression scenarios. This could be high dimensional or moderate dimensional, but P is usually very large. So I saw in some finance data why this P could be a few thousands, and number of observations could be hundreds of thousands. And in some biology data, it's a little reverse. The P could be tens or hundreds of thousands, and the N could be a few thousands. So there are situations both ways, and they're both real, and actually very, very, very much real. Very many people are interested in getting something out of this type of data. So we're interested in doing model selections in some sense, and one approach is to do simple regression or some kind of a penalized regression and trying to decide whether you have selected the right predictors or not. So the notation-wise, we think about say S0s are those coefficients corresponding to zeros. Those features coefficients are having been zeros. And S1s are those non-zero coefficient set. Our goal is to figure out which one belongs to S1, but we try to include as fewer from S0 as possible. And the so-called FDR control is to control that in your selection, the percentage of the variables you selected from S0 is bounded by a rate Q, or in probability, or in some asymptotic sense. We all will talk about. And we mostly will cover the linear models and some graphical models, and also some generalized linear models, and trying to see this data splitting approach, how it works. Next slide. For FDR control in the regression model, there's some early works based on this Benjamini Hodgkins procedures. Although these p-values are correlated, if they are not too highly correlated, their original procedure works pretty well. So especially in dimension when p is relatively small compared to n. But when p is becoming comparable to n, then the problem may occur when they're somewhat correlated. And there are some different extensions, but the extensions typically are different ways of coping with correlations, but they tend to be very conservative based on this modified BH procedure. There also early work on data splitting, which is to use the first half to do to find variables, and then you use second half to set up a p-values, and then you use that to do variable selection. That's still reasonable. So this approach is useful for high dimensions. But as you can see, once you do data splitting, you sort of weaken your signal in this case. So that's somewhat one price you have to pay. We hope later on I will try to see if you use multiple data splitting approach to aggregate all this splits information, you actually can get back the almost full information. The recent revolution was, as we all mentioned, by Immanuel Candice group, and they have developed a very innovative ways of doing this variable selection. I think, to me, there are sort of two key ideas from this approach. The general idea is to create fake variables, and the consequence of creating these fake variables, there are two. One is so-called self-referencing, meaning that you don't really need the p-value to tell you whether it's good or not or bad. You can do so-called self-referencing. For if it's a null variables, this particular variables, because of the null cutoff, should show some kind of a symmetry around zero behavior. And another one is somewhat make this kind of information independent. Next slide. So this is a brief introduction of this knockoffs in 2014 paper. They have many different variations afterwards, so I have no way to cover all of them. But interested people, please check their websites. They're very interesting progresses. And here is just say you can think about this pictures. The left is the real variables, the right is the fake ones. You create exact copy, not exact copy, sort of a fake copy with the exact size of the original X. And one way to make them is to make this particular covariance matrix design. And in this way, you can guarantee the so-called exchangeability things. There are a few approaches. One is more efficient than others, and over the years, people have had some nice progresses along this direction. But this is rough idea. And in low-dimensional case, you could do this exactly without assuming anything about the X. But in high dimensions, you may need to assume some joint distribution of the X's, or at least up to some nice exponential families. You have to make some assumptions in that way. The next slide. So this is the fundamental of self-referencing. That is, if it's a null variable, you create this statistics based on either knockoff or we do data splitting, so that under the null hypothesis, this is symmetrically distributed around zero. So this is marginally symmetric. So that's one thing. And also, so we mostly utilize this. Another one, as I mentioned, is somewhat the sign independence. That one we cannot achieve anymore because of the correlations. So another effect we would like this to have is the so-called signal strengthening. This is hard to achieve, but at least don't do too much signal weakening when it has a signal. So this is related to the optimal way of constructing this this particular statistics. Next slide. So the data splitting approach goes as follows. You just split the data into equal half, and then you can estimate sort of two coefficients, and we generally call the impact measurements. Really means if you are actually doing the neural networks, you can still measure these things, but it's no longer coefficients. It's really the influence functions. And then you can construct this mirror statistics by, I think this is pretty general. I don't know whether this is the most general forms, which is the sign of these two coefficients and multiplied a function of the absolute value of the magnitude of these two coefficients. There are some typical approaches, the most straightforward is this -1, but this turns out to be less efficient. There are more, I think this one was first observed to be relatively more efficient in the original Candice paper. And recently, some of my colleagues, Tracy Kerr, they have done some work to prove this is optimal under certain case. You can also think this is somewhat optimal from hypothesis testing. If you use Neyman Pearson lemma, you sort of can argue this is the best. If you think about this, this data splitting create these two copies of the beta estimates. And if you look at two-dimensional, they're just spherical Gaussian asymptotically. So if you do sort of hypothesis testing, optimal boundary will be just like this one. So it's not hard, but I will not give you details. The next slide. So once you have this kind of symmetry and you require something, so heuristically, you just need to use the negative tails to account for the false positives. So imagine you are cutting off at the boundary, which is tau, which is the statistics is tau. And those true signals tend to be large, positive. So that's on the red part. And the blue parts correspond to the false positives. You of course don't know which one is belonging to the blue part, but you can use the negative tail to estimate this amount. So that's the idea of knockoff, and this also the self-referencing, and the same here. Another thing we sort of need to assume that this individually is fine, marginally is correct, but if you want to accumulate them, like sum of all these quantities, you need somewhat weak correlation assumptions, which typically can be satisfied in high-dimensional linear models. And if you want to prove some asymptotic properties, those standard assumptions usually can imply this type of weak correlations. But even when they are highly correlated, as we tested, they still work, but we can't prove it anymore. Next slide. The multiple data splitting is also, as name suggested, you do this multiple times, and then each time you will have a collection of variables being selected, and then you try to assemble them together to get the coherent ones. The next slide. The next. So the way we assemble them is slightly different from what people have done for data splitting. And this one we introduce the so-called inclusion rate. That is, for each data split exercise, some were being selected, some were not. So suppose we only selected 100 out of 1,000 variables, and then each selected variables will give a weight of 1/100. That is 1 over the number of selected variables, and all the others will be 0. So for each selection, the total inclusion rate is exactly 1. So then for those variables, they tend to be selected more. So if you accumulate their selection rate, take average, they tend to be large. So you can order them according to this inclusion rate. And then you can cut off at the smallest ones at a certain level so that they sum up to Q. We can actually prove under some asymptotic property that this is pretty conservative. And if the single data splitting can keep this control, this FDR control, then this multiple data splitting will also be able to do that. And actually it's slightly better than the single ones, but how much better we cannot really quantify. So next slide. So this is illustration of this multiple data splitting effect. So this is very simple normal mean problem. So in this case, actually, the p-value is the perfect summary of the statistic. That's what we call as the full information. You can imagine you do the data split, you split in half, and you do this kind of mean estimate contrast. If you do one data split, it's very noisy. right? Because some by chance will be large, some by chance will be small. So if you look at this scattered yellow dots, these are sort of one data split. They sort of, this score are all over the place. They're very non-concentrated. But if you replicate this many times, you can see this is the p-value. They're almost monotone functional p-values. So that's nearly perfect recovering the full information. And these just illustrating the blue dots are those resulting from like 10,000 replicates. And this orange dots are 400. 400 is pretty good. In practice, we also compare the powers. Next slide. Next slide. So you can see that even with about like 400, 100, well, I don't have that slides, but usually with 100 to 200 data splitting, you can almost get saturated. You can't really get much more. So this is also power comparison for the normal mean problem compared to the this BH procedure, which is supposed to be the optimal in that case. And you can see this is almost indistinguishable. The blue one and also the gray one. So these are almost indistinguishable. The red one is the single data split. You can see clearly the power loss. The next slide. So for linear models, especially in both high dimensions, if it's very low dimensions, you can just do two independent OLS, the ordinary least square, then you do the contrast, that's fine. But if you have high dimensions, we usually suggest to do the lasso, but with relatively more loose lambda, but we want to be able to do to have so-called screening property, meaning you include all the relevant variables. And then you can use those selected variables from the first half of data to do the ordinary least square on the second half. Then you can construct this MJ for all the variables. And in this case, you can prove they are symmetric properties satisfied and so on. Another strategy is to use post-selection inference. You can also do that. We tried both. It seems to be not too much difference. The first one seems to be easier. The next slides. So we did some comparisons for different sizes of covariance matrix and compare with BH procedure and also the knockoff. As you can see, this is, I don't know how clear you can see. The top figures are FDR control. The nominal level is 0.1, so they seems to be all doing very well. And this block ones are some procedures from this Swiss group, and they tend to be very conservative. This one way of doing this kind of multiple data splitting things. You can see especially the weak signal case and also high correlation case, this multiple data splitting are doing well. So, but in relatively independent case and the strong signal case, the knockoff seems to be doing better. So that seems to be consistently observed in many different settings. Next slide. And this is a case where the assumption seems to be violated for almost all methods. This is reasonably high dimensions, but there's a constant correlation, meaning that all of them have equal correlation. That's the case. You can't, the correlation is really not weak. Eigenvalues were getting large. You can see this is the independent case. The knockoff is doing quite well. The MDS is not too bad. This is FDR control level. So the lower right corner will be better. So this one, the X direction is the power, the Y direction is FDR control. FDR levels, you want that to be low. And you can see in this is case where the correlation become large, 0.1. So MDS is getting lower FDR and also higher power in this case. The next slide. We also try some non-normal designs. This was the example has been tried in some of the knockoff literatures, which we used some correlation, the axis from this GWAS studies. these typically correspond to the SNPs, so they are not the continuous, they're actually discrete values. So it's not particularly normal, but they're not too bad if you have large enough, they're almost. So MDS is doing well in many cases, especially you can see the weak signal case. This is relatively weak signal case is doing quite well. So that's one thing we observe. We still don't understand why exactly and this multiple data splitting works seems to be able to recover these subtle signals in the weak signal case. Next slides. This is some non-Gaussian designs. The covariance matrix are the axes are simulated from T distribution or mixture Gaussian distributions. And this is a little unfair for other methods because when you assume they're normal, then this is misspecification. They tend to have errors. But this is just trying to show that multiple data splitting seems to be quite robust to this type of different design matrices. So you can see the MDS for this blue triangles, their FDR almost always under the control. Next slides. I don't know how much time do I have. Next, yeah, this is graphical model. I won't
give about 5 minutes.
Yeah. Next slides. Yeah, this is just result. Next slides. So this is about interest. I just want to mention this generalized linear model case. It's also inspired by, also stimulated by Candice's work. And as you can see, both of these works actually were communicated very clearly and very excitingly by his very fabulous students. One is this Pragya Sir, and another is Lucas. Lucas Jensen. I mean, so both of them were hired recent years, and then during their talks and their casual conversations, so we got quite stimulated, and especially my students were very excited to learn these things. And this is also a recent work. They found that in the moderate dimensional case where P and N are of the same order, so that's the P over N is converging to some constant between 0 and 0.5. And then the asymptotic results for the MLE in the nonlinear, in this generalized linear model is no longer the classic one. There's somewhat a rescaling effect. In other words, the center will be rescaled compared to the truth, and the standard deviation will also be rescaled. So this create quite some issues and problems in the classic inference. If you want to give a confidence interval, even asymptotically correct the confidence interval is not very easy to get because of this very tricky normalizing factor, alpha star and sigma star here. But we can actually using data splitting to do this without worrying about alpha star and beta, sigma star. Of course, we will not be able to give a confidence interval, but we can actually do this variable selections quite well because under the null, beta j star is 0, that's the true beta. Then the only unknown factor is sigma star. But sigma star, if you only use the symmetry property, not the scale property, then it's okay. So we actually are completely fine without knowing that if you're just creating a mirror statistics. So that's how it works. So the next slide. So if we use the data splitting, it works quite well. So this is the large P and N. And also this ABHQ is the adjusted procedure using p-values. That's actually adjustment based on this Candice and the Sir's results to adjust the correct scales, then it works the best. So BHQ has FDR out of control, so this gray squares should not be counted. But the best one, which is still under the control, is this ABHSQ. But you can see MDS is actually not far. It's very closely matching the results in this particular case. And also the next slides. in the case, like in some other models, negative binomial, I don't think so far we have known these rescaling factors. So there's no nice papers. Maybe Emmanuel already had a new paper on that, but that would be a different formula. But in this case, the MDS is still doing quite well without having to know that. The last, okay, next slide. So in the high dimensions, of course, we can do this so-called debiasing lasso. But somehow this debiasing lasso achieve asymptotic normality rather slow, but it achieved the symmetry rather quicker. The next slides. So this is the picture. So you can see if you use the normal p-value, it's pretty bad. That's the right top angle. But if you just use the symmetry, to create this contrast statistic, they are quite symmetry around 0. You can see the right lower figure. So because of this, if you use the data splitting to do contrast, it's actually doing quite well. The next slides. The MDS shows very good power compared to other methods. The knockoff somehow in these cases are not doing very well, but I don't know exact reasons. Anyway, so I probably, the next slides. Yeah, we tried a real data example, which has been analyzed also by Candice group. This is microarrays and trying to figure out which genes are particularly responsive in this different types of treatments and so on. So the next slides, I just don't have time to give you much details, but here is just the genes we selected, and the top half were also selected by knockoff. So we selected a set which is the superset of the set selected by knockoff. So basically double the size, and the right columns are some literature supports for the findings. There seems to be some support for our findings in this case. It's not completely sure yet, but it's somewhat sign support. Okay, so the next slides will be, well, I think it's an interesting work. I don't want to read through that, and it's stimulated by the great statisticians like Vin and also Emmanuel's group. And next slide, I'd like to acknowledge, so Lucas has been quite instrumental in stimulating us to think about this. And also Binyu's talk on this data perturbation has been quite also stimulating. Let's give us some basic ideas. So there are quite a few collaborators on this work, and they're all young and energetic. Thank you very much. I will stop here.
Thank you, Jun. Very interesting work. It seems like multiple data splitting is both reasonable and powerful, especially as the independence assumption fails and as you move to moderate to stronger correlations of the signal. So something to try out for sure. I'm gonna now turn it over to Emmanuel Candes, who, as you have heard, has worked and has pioneered actually the knockoff filters and has still been working on knockoff filters. But today he's gonna talk to us about something new: model-free, robust machine learning predictions, or conformal predictions, as he calls them. So I'm gonna turn it over to you. Thank you very much, Emmanuel, for being here.
Thank you very much. I'd like to thank the organizers, and especially John Leone and you, Edo, for inviting us. I enjoyed the talk by Jun Yu very much. I think it's fantastic work and it's extremely important. I've learned a lot from Jun when I was a student. Jun was a professor at Stanford when I was a beginning graduate student, and I've learned a lot. I'm still learning a lot from Jun. I'm teaching a Markov chain class where I use this fantastic book to stimulate students. So it's a pleasure to be in a panel with Jun.
Thank you very much.
Today, I'll talk about reliable and recent progress in predictive inference. Next slide. And, this was machine learning 15 years ago. The goal was to predict movie ratings. And I think in hindsight, we can say this, which is whether we got these predictions right or wrong, it did not matter. Next slide. But fast forward to today, we're using machine learning tools in extremely sensitive applications. For instance, for facial recognitions and drivers, and you've heard the problems associated with this. Next slide. I'm not sure if you know about this, but probably you do. People use machine learning tools to assist judges in US courts to make decisions. For example, there are companies who sell products, essentially criminal risk assessment scores, to help judges make decisions about who should get paroled, who should get bailed. And it's very hard for me to think about a more critical application of machine learning, a more sensitive application of machine learning, as it directly impacts our lives. And so, next slide, please. Of course, AI has a lot of promise. We are being sold that AI will improve medicine, will improve healthcare. And people use deep learning for medical diagnostics. And I think in automated healthcare, I think we should learn when we need to pass control to a human doctors when the diagnostic of a network, the confidence of the diagnostic of a network is low. But how do we know that a deep learning architecture, which is very opaque, is well calibrated? How do we know that its confidence is low? And so I think it becomes extremely important as we deploy machine learning to work on more and more sensitive applications that impact our lives directly, to be able to assess uncertainty a bit better and to understand when is it that a deep learning or a gradient boosted machine has low confidence in its prediction. And so as a toy example, we can imagine that we are a university like Stanford or Harvard, and they want to recruit students, and they gather a lot of features about each applicant, and they're going to try to perhaps offload some of the decision to a machine learning system that would predict how well this candidate will do at Stanford. And perhaps the deep learning architecture will spit out a score of 3.62. But then how much confidence do I have in this prediction? And the way I would like to think about this in this lecture is through predictive intervals. So this is very easy to follow lecture, I think. The way we're going to think about this is we need reliable systems. We need to understand that when the cost of a wrong decision may be extremely high. And so traditionally in statistics, we like to produce confidence intervals. So here we're not going to talk about confidence intervals about parameters. We're going to talk about predictive intervals, about future observations. And so what I would like to see more often in the way data scientists and AI researchers communicate the outcome of their research is in the form of these predictive intervals. So I would like to have a prescription, which is that it's not enough to give me a point estimate. You have to give me a range. And I want this range C of X, that is a predicted range of labels. For example, in the case of my student, it would be the predicted range of a GPA after 2 years at Harvard, let's say. And I would like this range to be accurate 90% of the time. That's a prescription. And I think we all agree that as the consequences of our decision impact people's lives, this is extremely important. Now, why do we not see this more often? Next slide. I think we don't see this more often because we are way past simple regressions, for which we have learned simple formulas to actually construct these predictive intervals. We use methods that are quite opaque and are very powerful, but it's not easy interpretable. And there is a whole lot of research that I will not talk about in this lecture that shows that somehow that this method can be really badly calibrated. But I think one of the reasons we do not see predictive intervals is that we use very fancy algorithms that by all means we should almost treat as black boxes. Next slide. Yet we'll see something a bit bizarre in this talk, which is that it is possible to construct predictive intervals that are valid no matter what the distribution of the data is, no matter what black box you're using. And this is work that was done with Yaniv Romano and Evan Patterson last year. Next slide. Now, this is something concrete. You'll see a method that is concrete. And I was pleased to see that actually it was picked up by the Washington Post, by the fantastic work of John Chirian and Lenny Bronner. Lenny Bronner is a data scientist at the Post. John Chirian is a Stanford student working for the Washington Post. And they use a method that I'll present to actually project results on election night. I'll say more at the end of the talk about what they've done. But I've been informed, and of course, during the night of the election, I watched the projection from the Post with, with my heart beating, and I was informed by the news desk that the model worked very well. Next slide, please. So, what are these prediction intervals? So, in abstractly, what we have is we have a bunch of training data, as is common in machine learning, and we have a test point. So, the features Xi's, in the case of my applicants, might be, which high school you went to, what were your high school grades, your ACT scores, your level of physical fitness, extracurricular activities, information about your parents, siblings, whatever. And Y is a sort of a quantitative measure of how you'll do if Harvard, say, were to admit you in its prestigious university. So what we'll do is the goal is to construct a predictive interval, a set C of xn plus 1 that contains a true label 90% of the time. And we don't want to make any assumption about the distribution of xy. We don't want to make assumption about the sample size. We want this to work always because the stakes are high. So in plain language, we want to say that based on the candidate's high school identifier, GPA, ACT scores, and everything I can have measured about an applicant, I would like to predict that the GPA range will be between 3.4 and 3.8. And I want this prediction to be correct 90 or 95% of the time or whatever. Next slide. Okay, so I just want to start with, suppose you had solved the problem. So what does it mean to have solved the problem? It means that suppose you know the distribution of y given x. Okay, so if you knew the distribution of y given x, you can see that, I don't know if you see, do you see my mouse? Probably not, right? You see it? No. So you can see that at every value of x, you would know the distribution of the response given x. And therefore, you could compute the lower quantile and the higher quantile of this conditional distribution. Next slide. And you could connect them to get, for each value of x, a very valid predicted range because you know the distribution of y given x. So I gave away the problem to you, and you compute the quantiles of the conditional distribution of y given x, and then you connect them. Next slide. But this is too easy. I don't know what is the distribution of x and y. All I have is this. What am I supposed to do? So we're going to do two things. Next slide. We're going to connect two areas of statistics. One is quantile regression, and this is a fantastic paper. So if my talk can be anything, it's just an encouragement for people who listen to me to read this wonderful paper by Roger Conker and Gilbert Bassett from 1978 about quantile regression. Next slide. So, okay, so I see the math did not come out too well, but on the PowerPoint translation, but I hope you can try to see what this is. So we're gonna try to formulate the learning problem as a regression problem. And so instead of using your usual squared loss, I'm going to use a loss which is called the spin-ball loss that you see on the right. And on the right, you see something that looks like the absolute value function, except that the slope may not be the same. And this is a loss that function, when you use your neural net or your gradient boosted machine with a loss function like this, will actually try to find the conditional quantiles in your data instead of the mean. So if we use the squared loss, then of course we're fitting the regression function. But if we should fit one of these losses, we're going to try to find the conditional quantiles in your data. So I'm suggesting that we're going to use this very fancy algorithm that we've talked about before, neural nets, gradient boosted machines, not with the squared loss, but with this loss to actually try to find the quantiles in the data. And so what you could do is we try to do this. This is a quantiles fitted by some method, and then we fit the lower quantile and upper quantile, and we hope that this will approximate the true quantiles. Now, is this valid? Next slide. And it is not valid at all. In fact, for those of you who have experience with neural nets, and we certainly fit a lot of neural nets at Stanford, you know, neural nets might actually go to zero training error, which means that the two quantiles will be the same roughly. And so you can imagine that your out-of-sample performance will be a disaster. In this case, because we were trying to be careful, it's not a disaster. It's about 66% coverage. You want 90, you got 66. Obviously, your quantized estimate are too optimistic. Next slide. So what we're going to do is we're going to take this first impulse and we're going to wrap around it. And we're going to build a wrapper around the, you know, a neural net quantile estimate machine to actually make it calibrated and make it valid. And as we'll see, the method we propose will work no matter the sample size, no matter the dimensionality of the data, no matter the black box you use, no matter the distribution of the data. Next slide. So how's this going to work? So there are many versions of this. I'm going to present the simplest version, and then whomever is interested, Ido was kind enough to collect references, and so there are lots of variations on what you'll see in the references that are in the library. So you give me a data, I'm going to split it in a proper training set and a calibration set. Okay, so the proper training set is on the left, it's in black, the calibration set is on the right. It's a bit like what June was saying, it's a bit of a data splitting step. You don't have to do it, but it's simpler if I present it this way. Next slide. On the first set, you actually run your quantile regression estimate. But now we know that it's not going to work. So we're going to see how well it does on the calibration set. And we're going to score how well this does on the calibration set by scoring each individual point. Next slide. So we're going to score individual points, and a point will receive a positive score or negative score, depending on whether it's within your prediction band or outside of your prediction band. So you're going to have a positive score if you're outside of the prediction band, and a negative score if you're inside the prediction band. All right, next slide. And how these scores are constructed, it's very, very easy. So if you're outside, I'm going to look at the nearest boundary, and that's your score. If you're inside, I'm also looking at the nearest boundary, but I put a negative sign. Okay, so let's say that we have 300 points in the calibration set. Therefore, we have 300 scores, and these are signed distance to the nearest boundary. Extremely simple. So now I have 300 numbers, and what do? I take the 90th percentile of these 300 numbers. So I'm looking at the 270th largest values of these percentiles, and I'm going to return as my prediction band whatever I fitted with my neural nets, but adjusted by this Q. I'm going to subtract and add Q. Now let's understand what this is doing a little bit. So suppose by some miracles, the neural net was actually fitting very good quantiles to start with. Then 10% of the point would be outside, 90% would be inside, and therefore the 90th percentile would be roughly 0, in which case I would not touch the great job that the neural net has done. But suppose the neural net, as is often the case, is too optimistic it's too confident about its predictive power. The thing will be too narrow, and so there would be more than 10% of the points outside. And so therefore, when I look at the quantiles of these scores, it will be positive. And so what that would mean is I would actually enlarge the width of my prediction band. If you're, on the other hand, a bit like June and myself, you're a bit conservative because you were well-trained, maybe you start with quantiles, and that's kind of an interesting point. You start with quantiles that are a bit too conservative. You want 90%, you get 95%, in which case your value Q would actually be negative, and you would actually shrink them. It says, no, Emmanuel, you followed yourself, you're too conservative. You don't need to be that conservative. You would actually shrink your estimate. Next slide. Now, when we use this procedure on the same data set, it's too good to be true. I want 90%, I get 90.09%. So this is quite remarkable. Next slide. Is this an accident? No, it's a theorem. And the theorem is that you can prove that this method, which is very, very simple, as you can see, achieves 90% coverage, almost exactly. That is, it's a theorem that the coverage of your predictive interval is at least 90%. That is, your predictive interval will contain the true response 90% of the time, and no more than 90%. And again, it applies always. Next slide, please. Now, what I'm not saying is that this is building up on the work of Vladimir Vovk, who is a person I admire. He's working in England, at Imperial College, I think. And so what we're doing is we're marrying quantile regression with ideals for conformal inference. Next slide, please. I think Vovk got a lot of things right, almost everything right, but maybe not the last part. And so what Vovk was advocating is to fit, and again, the math did not come out right on the translation, but basically you fit a neural net or you fit a learning rule by minimizing the squared loss, you compute the residuals, and then you build the prediction band by actually looking at the prediction at a new test point plus or minus the quantiles of the residuals. And the reason I think it's not exactly the right answer is that, as you can see, your prediction interval has constant widths, right? So it has a center, which of course depends on where you are. It depends on your regression function, but the width is constant. And that's not capturing the heteroscedasticity that we have in the data. This is going to be made extremely precise on the next slide, please. On this plot, where we have a very heteroscedastic data set, where essentially the conditional variance of y given x changes as a function of x. And you see on the left, you see the Vovk approach, which is essentially fitting a prediction interval of constant width with the CQR method that I'm advocating, which you see that somehow the width of your interval depends enormously of where you are in space. As a result, it's a theorem that both methods achieve 90% marginal coverage, which is what you see empirically. But the reason, like what we adaptive means that the method we have has much shorter length, so it has more informative intervals. Next slide, please. So the right picture is essentially a length of the interval produced by these two methods as a function of x. And so you can see the blue curve is our method, the CQR method. The red curve is Vovk methods. Vovk method produces intervals with constant widths where we are highly adaptive as to where in x. Now there is something which is very interesting here, which is also check the conditional coverage as a function of x. And the blue curve, which we see on the left, achieves almost a lot of conditional coverage, no matter what the value of x is. But the Vovk method doesn't. And sometimes it undercovers, sometimes it overcovers. And you can see that in finance application, if we can go back one or two slides. Go back one slide. Yeah. One more slide. Yeah. So if we go back one more slide, I think one of the problem is, suppose that the data is heteroscedastic and you actually build confidence prediction interval based on the size of the residuals, the quantiles of the residual. Suppose you're in finance, because I think that's one of the themes of the conference. Suppose you're in finance and you have periods where you have high volatility, period where you have low volatility. I think what the Vovk method will do is will tend to undercover in the high volatility because the response is more spread, and it will overcover in the periods where the volatility is low. So as a function of volatility, you'd either undercover or overcover, while the method we propose should be far more adaptive to the level of volatility, because it's what you fit when you fit your quantile regression. So let's go back 2 slides. Go up 2 slides. Forward 2 slides. Yeah. One more slide. Yeah. So we actually did a lot of data analysis. We used these methods, which are implemented, which I'll give you links to website where you can actually download Python and R packages to actually predict utilization of medical services. This is one of the data set we looked at. We have lots of covariates, age, marital status, race, poverty status, and so on. And the goal is to predict healthcare system utilization, for example, as measured by the number of visits to a doctor's office or hospital, and so on. It's a high-dimensional data set with 140 features and 16,000 subjects. Next slide. We use one of this extremely sophisticated method of neural net regression with a pinball loss. We use this TQR method. And so it's a theorem that both Wolf's method and our method achieves marginal coverage. This is what you see on the left. In terms of conditional coverage, we do better. And in terms of lengths, we do better. So we produce intervals that are more adaptive. They're shorter. They have better conditional coverage. And they have exact marginal coverage. Next slide. So this is if you're interested in healthcare, but we looked at Facebook data. We looked at a lot of data from science, and you can look at the paper. And so what we found is that this method was helpful, would outperform traditional methods in 10 out of 11 regression data sets that we actually have looked at. All right. There is an extension, next slide, please, to discrete labels. And how much time do I have left, Edo?
About 5 minutes.
Okay, so I have 5 minutes. So maybe this is instead of discussing these extensions to discrete labels, maybe I can just tell the audience that, of course, there are lots of problems where the response variable is categorical. What kind of objects do I have in front of a car if I'm interested in a self-driving car? And you would like to be able to also return short predictive sets in classification problems. And we have extensions of the method that you've seen to deal with categorical variables. In the interest of time, I will skip this slide and the next. So next slide, next slide, next slide. This works well. And I will just wrap up to go back to election night. So next slide, please. Yes. So again, I want to emphasize that this is not really my work. This is the work of John Cherian and Lenny Bronner. I think I mentioned before that John Cherian is a student at Stanford and Lenny Bronner is a data scientist working at the Washington Post. Next slide. So these are the kind of information you could see displayed on the Washington Post website. And so, the Washington Post, and this is the Washington Post, November 4th at 11:50 at night. And so this was the state of Pennsylvania, which, as you know, was a very contented state. And so the Washington Post was issuing predictions based on the model. Next slide, please. And so what you can see from the next slide is very early on, the Washington Post was able to predict, if you look at the left panel, that Biden would eventually win Pennsylvania. And so they had a very good way of actually displaying prediction intervals by using a very delicate color scheme. And they also were able to break the prediction in terms of the kind of county that you were. And so, so this is the kind of information that the Washington Post displayed running the method you've seen. Next slide. This is a few days later, November 7th at 8:30 a.m. Of course, the prediction became tighter because we had more data. Next slide. And, now quite a bit of confidence that Biden would be ahead when the count is finished. And so, as I said before, the model worked quite well. So next slide, please. So, okay. So I had prepared some slides, but they were translated, and so somehow we don't see them very well. But basically, the way, just to give you a sense of what was on this slide. So the way the Washington Post looked at this thing was that counties are going to start reporting, right? And so for each county, we have a bunch of county features, demographic features, whether it's an urban or not urban, and so on. And so the Washington Post was interested in predicting 3 types of outcome. One is the voter turnout in 2020. And to do this, they defined a regression variable, which was the voter turnout in 2020 minus the voter turnout in 2016. And then they were interested in the number of Republican or Democratic votes, which we're going to write RI20 or DI20. So this is the number of Republican votes in county number I in 2020, and of course, the number of Democratic votes in the county number I in 2020. And as a regression variable, they use the fraction, the difference in the rate for which you vote for Republicans and Democrats between 2020 and 2016. And now counties start to report. So you see variables. So you see the data from a few counties, and you have missing counties, and you're going to use the method you've seen to actually predict to actually build up confidence prediction interval for the counties that have not yet reported. Now, there's one thing that should make you worry. Next slide, please. It is, are counties being reported? Are we drawing counties out of an urn? And no, we are not, because the counties actually do not appear in random order. You know that maybe some counties with some characteristic report earlier than others. So the data is not exactly exchangeable. And that's where the thing breaks up a bit. But, you know, I'm not going to go through the details of what was done, as opposed to actually deal with this issue. Because you had access to previous elections, you could see by playing the movie of the counties in the order in which counties show up, you could adjust the confidence level to make sure that all through the night and the ensuing days, you maintain coverage. So the only assumption we make here in this talk is that the data are shown to you in a sort of a random order. It's not exactly the case, but the Washington Post came up with a very clever way to adjust the inference to deal with the ordering based on previous elections. Next slide. So if you're interested in this, there's a website and code. I think June said it nicely. It's important to be transparent and reproducible. And so people can download and reproduce what we've done. Next slide. And I think my time is up. So I showed you a method to basically get reliable predictive intervals. I think it's extremely important as we deploy machine learning in very sensitive applications. The election is one of these sensitive applications. It's important to get it right. I listed quite a few references. If people are interested in the theory and the work of Vladimir Vov, there's his book, Algorithmic Learning in a Random World, that I recommend everybody take a look. It has changed a bit my life. And so with this, I'll pass it on to you, Edo. Thank you very much, Emmanuel. Very cool method. Again, one more innovative, very cool method. Like June, I'm a big fan of your work, as you know, and for everyone, Emmanuel is very understated and very modest, but he only combined a couple of ideas that existed out there, but clearly, he knew which two ideas to combine and exactly how to combine them to fix the issues and apply them to a very important problem. So, well done. Thank you for sharing your work with us. And Vovk reference is listed, by the way, on our content library. So please, with the link. So please take a look. Thank you again. Now I'm going to turn it over to Panos. Panos is a former student at Harvard, and now he's a professor at the University School of Business in Chicago. Happens to be one of my outstanding students. So Panos, welcome, and thank you for being here. I'm going to turn it over to you. I think you're going to tell us about a couple of new things that you've been working on to control errors.
Okay. Yes. Hi. Thanks for the kind invitation. I'm really happy to be here. I'm also humbled to be in the presence of such distinguished speakers. So Edo, be prepared to be disappointed. So today I'm talking about a new method, a new approach to doing inference. It relies on the randomization framework first developed by, it does originate in Fisher's work, but it was formalized by Lehman and Romano. Next slide, please. My setting is pretty simple. It's the standard regression model. We have y with the responses, x's are the covariates, beta are the model parameters, and epsilons are going to be our errors. This little omicron that you see over there, that's kind of an error in translation. This will be epsilon. So the betas are going to be our object of inference. We'd like to do inference here, but our key departure from the classical frameworks, the classical approaches, is that we're not putting any assumptions yet. And part of the proposal in this work is that we just don't rush into making these assumptions, so that we try to make inference, to develop a mode of inference that is as flexible as possible. Next slide, please. So just a review of those standard approaches. Of course, there's the parametric approach. We just have a model for these epsilons. We derive some estimators, let's say OLS. We do some mathematical statistics, CLT, and then we say we can use these asymptotics to do inference. Or we can do Bootstrap, which is a non-parametric approach. We can either, and there are two variants of that. We can either resample the entire rows of our data. That's the pairs Bootstrap. Or, and less well-known, but actually better in practice, is to Bootstrap flavor is when you fix the x's, the covariates, and then you resample the residuals. And that was pioneered by the pivotal work by Friedman and Lane. However, both approaches require some form of extensibility. In many cases, in most analysis, you have assumptions about IIDness, some assumptions about the x's. And both of them cannot handle easily complex error structure. And this is at the core of this proposal today, is to try to address the more errors that are, or like problems, data that have a more interesting, more complex structure than just plain IID or plain extensibility even. So both methods rely on approximations. They do rely on asymptotics, and in most cases, they do rely on well-behaved estimators. So the proposal I'm going to discuss today can work even under ill-behaved estimators, even inconsistent estimators, for that matter. Next slide, please. So am I saying that something is wrong with Bootstrap? No, nothing. There's nothing per se, right? This is the most important, one of the most important statistical tools. However, the main critique that I'm developing here is that it was introduced as, since inception, it was based on uniform sampling. So when you try to accommodate, to address complex error structures, you need extensive modifications. So that's why we have so many flavors of Bootstrap. We have residual, wild, cluster, block, stationary, pigeonhole, multiplier, Poisson. It's just a whole zoo of different Bootstrap flavors. So, and I think and that's my philosophical take, let's say, is that the Bootstrap starts with a procedure, right? It starts with this resampling. It starts with what you have to do with your data, and then goes ahead to accommodate your particular problem structure. And my argument is that it should be the other way around. First, we have to think about what the structure of the problem is, and then think about what procedure to use. In some sense, Bootstrap has always been this heavy hammer in search of nails, right? And sometimes we have to duct tape a screwdriver around it. So next slide, please. So what I mean by when I say complex error structures, well, in practice, we do have complex dependencies, okay? So, and we do require, and most methods require some form of invariance assumptions on these errors, even implicitly. In most cases, these assumptions are implicit. Some form. What do I mean by invariance? Well, when we assume that the errors are IID normal, that's already an invariance assumption that we are making. But that's not as primitive as assuming, let's say, that the data are extensible, like the errors are extensible, which can happen when the errors are being generated under identical conditions, for instance. The errors might not be extensible, but that might be sign symmetric, or they might be clustered. Suppose, for instance, you get observations from different firms. And there might be clustered, your data might be clustered by firm, or the data might be clustered by the geography. You might have a time dependence, that's an autocorrelation structure. Or they might have double clustering or triple clustering. Suppose you have panel data where these are clustered by the firm, by time, by geography, etc. So there's all sorts of invariances, all sorts of structures that can appear. And unfortunately, right now, we need a new method, a different method for each one of these different structures. So my promise here, or at least the promise of this approach, will be that it's to develop a unified way to address all these heterogeneous settings. Next slide, please. So what is the proposal here? What are we going to do? First of all, it will be just a different way of thinking. Like, first of all, we'll try to think about what invariance assumptions are matching with our problem structure. So before we even begin thinking about the procedure, first we have to define what is the error invariance that we're going to base our inference on. For that matter, we're going to assume that there's a group of transformations G, where your errors, if you apply these transformations on your errors are distributionally equivalent. It doesn't invariant. The distribution doesn't change for any transformation from that group. For instance, extensibility, something that Emmanuel mentioned before, is basically you kind of shuffle your data, you shuffle your errors, and the distribution doesn't change. And these are assumptions. This is a more primitive assumption than assuming IID. It's like a weaker assumption, right? Or when you're assuming normality, you're assuming extensibility, but your IID normality, you're assuming extensibility, but you're also assuming sign symmetry and other sorts of more primitive invariances in your data. So in this case, in going back to that extensibility, in this case, this capital G, script G in the original slides, is basically the symmetric group. And the algebraic structure, the fact that this is an algebraic group is important for the validity of the methods going forward. Now, this G can be anything, right? You can have some weird structure. It can have like time dependencies, you can have cluster dependencies, double cluster dependencies, etc. So in this case, naive bootstrapping cannot longer work, right? You cannot go ahead and just start permuting data and expecting that this is going to work. And that's not a failure of the bootstrap. It's just is more like, I think, a failure of our understanding that it's really the problem structure that matters, and it's not a question of what procedure to use. Going forward, this G, I would call this inferential primitive, because this will be the important object that will basically inform the inference. Going forward, the idea will be that the analyst is going to define what is the inferential primitive for the particular problem, and then more or less the procedure will be defined after that. It will be determined after that decision. So this is the promise of unifying all these different settings under like a common inferential framework. So next slide, please. So the general idea is as follows, and this will be an infeasible, an idealized procedure, but I will make it concrete in the next slide. So suppose we have, again, this regression model. We're not making an assumption about the errors. I'm not assuming they're normal. I'm not assuming they're IID, but I'm assuming that they do satisfy that that invariance. Okay, in that with G being the inferential primitive. And suppose we have some hypothesis to test on the betas. Later it will be a linear hypothesis, but let's keep it general for now. There are two key components to the idea here. One is to have a test statistic such that under the null hypothesis, your test statistic is a known function of the errors of your regression. So that's the first thing. And this is not so such a strict of a requirement. In most of my implementations, this test statistic is basically the OLS. It's based on OLS. So you can, based on classical OLS theory, you can show that this condition can be satisfied easily. Now, suppose now that you can take that function, this T of n, and you can just take these errors and apply those transformations at random. Let's call this capital T, and then in the second component, the second part of that method, just calculate the p-value using that capital T with respect to whatever you observed in data, the observed value of your test statistic. Now, standard normalization theory by Lima and Romano suggests that this p-value is exact for testing the null. And the proof is very straightforward. You can show that whatever randomization statistic you have over there, this capital T has the same distribution as your test statistic, just which follows from the invariance property that we have already assumed. The group property of this G is also important, and that's part of this. Just to keep things simple. And I should say that at this point, that randomization theory is maybe a misnomer. It doesn't have a good PR. When we say randomization theory, randomization test, this does not require an actual randomized experiment. At the heart of that theory is really the invariances, the group invariances, and not the actual act of randomization. But it kind of comes from Fisher. It was developed according to that language. So it's called randomization theory right now. And actually, conformal inference is an extension of the, or is part of the randomization framework as well. Okay, so next slide, please. So here's a concrete example. As I said, this is an infeasible method. It's using the actual errors, but these are unobserved. So what can we do in practice? Well, suppose we want to test a very kind of simple significance test on the jth component of your unknown parameter. Suppose we want to test that beta j is equal to 0. What do? Well, first of all, assume that beta j is equal to 0, solve the restricted OLS, and get your restricted residuals. So the idea will be basically just plug in those restricted residuals in the procedure that I mentioned before. Your test statistic, how to satisfy that condition on the test statistic? Well, just take the regular OLS. Standard theory will tell you that under the null hypothesis, this is a known function of your errors, and that Pn function, you can see it over there. It's a classical projection on the standard projection on the column space of x's. So that condition is satisfied, great. And then we just plug in those restricted residuals and we calculate the p-value out of that. And so our decision for the null hypothesis for the significance test is basically depends on that p-value. It's as simple as that. Okay, it just relies on simple OLS and restricted OLS calculations, and this you have to make that assumption of the error invariances. Just a quick note about the theory. Next slide, please. Just to kind of show you what is the promise in terms of the theory. What do we what is this method is doing better? Like why do I think that this method is going to be more robust than other approaches? Well, the main condition for the validity of this test, by validity I mean that just controlling the level of the test under the null, is that this condition in equation 1. So if this condition in equation 1 holds, then the test is asymptotically valid. Now this condition has 3 weird terms, but I can give you the intuitions behind them. I can show you why I believe this type of approach will be more robust and hopefully will kind of open up new ways to do inference. So this term 2 is actually is a term that quantifies the richness, if you will, of this set of invariances. The inference will break. The proposal that my proposal here will break. For instance, if these transformations you're making are not rich enough. Let's say that instead of permuting n elements, you just permuting only 2 of them as n increases. Of course, you don't have too many permutations involved, so it's not this set is not rich enough. This richness is not a formal term, but it just kind of shows you that the type of transformations you're making, that complexity, it does affect the validity, like the extent of your inference. This term 3 over there that you can see is basically, you can think of it as your transformations preserving the information structure. This inverse, you probably recognize the Fisher information there in that expression, term 3. So intuitively, kind of all these things together, they kind of tell you that your estimator, which is term 1, your richness of this transformation you're making, your referential primitive, and how this relates to the information structure of your problem. All of this have to interact in a synergize so that you get that asymptotic validity. I think the important another important point here is that this term 1 doesn't have to go to 0. So basically, this method can work even with inconsistent estimators, even with ill-behaved estimators. So for instance, suppose that your errors, the variance of your errors increase with n. It can happen, right? Like the more data points you collect, perhaps the more noise is being introduced. In this case, the OLS is not squared n consistent. It might be not even n consistent, right? So it doesn't matter. Well, the important thing here is it doesn't matter that you have a consistent estimator. What matters is that synergy between all those elements, your estimator and your inferential primitive. Okay. Next slide, please. And the next one for the rest of this presentation will be mostly examples, kind of illustrate to you the logic behind this and what I think is kind of new and novel and useful about it. Suppose we have clustered errors. Suppose we have a very simple regression model like the one that I had over there in this display. The axes are just simple, just from 0 to 1, and the errors are clustered. So there are 2 clusters. One cluster, the variance is very small. When x is your covariance is like less than 0.9, and above that threshold, the variance is much larger. So in this case, of course, the data are not exchangeable, like your errors are not exchangeable. They are exchangeable within clusters, though, and that's the key structure that we can utilize. But if you do just run naive OLS, then you will see that we just fail to detect significance. And not only that, this interval is tilted to the wrong direction. Now, but in this case, the structure is obvious, right? We can have extensibility within clusters. So if we had that knowledge, then we can just apply that method, this residual randomization method, where instead of just doing this resampling of the residuals kind of uniformly, we only do this resampling within the particular clusters. Okay, so next slide, please. So if you do that, if you just define your Z, your inferential primitive, as permutations within those clusters, then you can test your significance. You can have your you can implement your significance test. And not only that, you can run a test for any value of your slope. As you can see, that you can for different values of that beta in this null hypothesis, we can generate a p-value. And this is the so-called p-value plot, where you can cut it horizontally at like 0.025 or like 0.5, depending on what is your targeted significance. And then whatever remains, what's below that plot, will be your confidence interval. This is called test inversion, and it can give you. We can use that method to invert it to get confidence intervals as well. So in this case, the confidence intervals that comes from this more using this type of resampling that's more adapted to the problem structure gives us a confidence interval that's 0.03, 0.025. It's not exactly centered at the true value, which here is 0.2, but it is close, and it's definitely better than the regular OLS, of course. Okay, and the reason, of course, is it should be no surprise. We're just utilizing the structure that is inherent in this problem. Next slide, please. Here's another structure that might be more useful for financial applications. Suppose you have autocorrelated errors. Suppose that the errors in this case might have an AR structure, but might even be non-stationary. So what can you do? Well, there are several robust error methods for that. There are hack methods, heteroscedasticity, autocorrelation, consistent methods in the literature. There's also the block and stationary bootstrap methods that are available. However, all of them, both of them are not robust to strong dependence, like to kind of strong autocorrelations. They don't work very well in small samples, and also very, very sensitive to your covariates as well. If your covariates have notoriously, if they have heavy tails, then these methods are not going to perform that well. So what can we do here? What type of invariance can we exploit here in that type of problem? Well, there is one. If we stare a little bit into that autocorrelation structure, just one type of invariance comes forward. Next slide, please. So with that simple model, then what we can say is that if we condition on some epsilon being 0, then what comes next is going to be sign symmetric. Okay, and that follows immediately from this AR structure, essentially. Okay, so the idea here will be that, well, let's define an entirely new inferential primitive where we're going to look into a residual plot like that. And instead of just resampling like what naive bootstrap is doing, we're going to do this reflection around the time axis. And why can we do that? Is because we are assuming that the structure of the errors have this particular AR form. Okay, and so the idea here is basically to say, essentially to say that this G, this inferential primitive, are basically just reflections around that time axis, and then this type of transformations in our residuals will give us. Basically, we just plug it in our procedure, and will give us in our inference. And by the way, this type of procedure can be applied even with errors that are non-stationary, which we don't have good methods right now for that even. Next slide, please. Here's just one example of how this method works. I have the errors. They have a simple autocorrelation structure. I look into errors that have like normal innovations, even like a mixture innovations. I look into cases where we have covariates that are IID, that are autocorrelated, and also that they have thin tails, or they have heavy tails. And there's just too much happening here. I cannot point your attention. I don't have the pointer. So let me just say that the reflection test, this residual randomization method, it is robust across all these different domains. And it is because, first of all, we're conditioning on the x's, so the heavy tails of this covariance is not a problem. And second of all, we're just using that AR structure correctly, right? We're just adapting to the problem structure. Whereas if you look at OLS, of course, it's going to break because it doesn't work under under the settings. But also the hack errors are quite sensitive to whatever errors distribution of the errors you have, and also whenever you have thin-tailed covariates or you have heavy-tailed covariates, you can see that it diverts a lot beyond this point of 0.05, which is the nominal coverage. Okay, so just one final example. Next slide, please. Just a cherry on top. Suppose we're seeing that in an entirely new application. Suppose we have data with I is going to be firm, time is basically a time, and we do have just a very simple kind of a panel, like a panel data model. And we do have X's that have an autocorrelation structure, and they also have log normal errors, which are heavy-tailed. Suppose we have errors they do have this autocorrelation structure, but they also have random firm effects, and they also have normal errors. So what are we going to do now? It's a very complex model. There's a very complex structure. What method are we going to apply? Are we going to use Bootstrap? Are we going to use block Bootstrap, hack errors? Are we going to do Fama Macbeth errors? Well, just try to adapt to the invariances in your problem. Next slide, please. Actually, what you can do here is, if you one observation is that if you demean over time your errors, now these have the autocorrelation structure that I presented earlier. So just use the reflection invariance this gref that I presented in the previous slide. So that's one. Okay, so in our resampling, what we could do, we could just take the residuals, average over time, subtract for the actual residuals, and then do this reflection test. That's one idea. If the innovations in the random firm effects are extensible, then we can actually also exchange the rows of this residual matrix. Okay, so both of these can work, assuming that under the assumptions, of course, of correct invariance. Here's simple simulated study: 5 firms, 200 data points, strong autocorrelation, and suppose these firm effects are T with 5 degrees of freedom. OLS breaks, of course. If you do a simple hack version where you just average over firms and then you do hack robust errors, it is better, but still very much over rejecting. The correct level here is 5%. And if you look into the residual normalization method based on these invariances that I presented earlier, you can actually get to, these are all of them valid, and the one flavor that's what I call conditional is actually very close to the nominal level as well. I don't have time to describe the difference between a conditional and conditional, but I do have that in the paper if you're interested. And the code for this particular example, just you can download it, you can play with it, just load it and just run the main simulation. You'll see how this exactly works in practice. Okay, so next slide, and that concludes for me. I talked about residual randomization, which the main promise here is that it is going to address inference in regression models with complex error structure, be it one clustering, double clustering, autocorrelation structures. If you look into the idea is that you look into what invariance, what problems, what kind of structure might make sense in your problem, and then you kind of take that and then you plug it into this residual normalization procedure. And in that sense, it addresses inference with these complex error structures in a unified way. Okay, so instead of starting with the procedure and then thinking about the structure, we start with the structure and then thinking about the procedure, which I think it's a better approach. If you look into the paper, there are like extensive comparisons to several flavors of Bootstrap, several flavors of robust error methods. So what I think is a notable feature of this approach is that the same exact procedure is being applied to widely different settings with clustering, double clustering, autocorrelation, etc., and even high dimensional regression as well. For each one of these settings, there's a different method out there. So we have to develop a different method. Where we're here, in contrast, this type of approach gives you the same procedure for all those different settings. So hopefully you can see some value in it, can try it out, and perhaps it opens up like a new mode of inference that's more flexible. Next slide, and that's it. So if you're interested, there's some more information. I have a working paper. There's an R package called RRI. There's a technical report that kind of walks you through that package, and there's a link there for if you're interested more in that. And I should repeat as well that example with the this panel data structure. You can find in that link on that slide. So thanks for your attention. I hope it didn't go over time, Edo. But thanks again.
Thank you, Panos. Can confirm you did not disappoint. Very good job. So I'm very excited about all these new ideas, cutting-edge ideas, very simple, multiple data splitting, conformal quantitative regression, and residual randomization, or maybe residual invariant resampling procedures. They're very simple. As you've seen, they're very powerful. And all the references to papers, to code, and to other resources will be posted in the content library page of the event. So let me conclude by thanking our distinguished speakers again on behalf of the Statistical Science Department and the Fox School of Business at Temple University. Thank you very much for being here. We really appreciate your work. Thank you. I'm going to turn it over to you, John.
Thank you. The primary objective of Wells Fargo and our partners at Temple is to build a collaborative community between practitioners and academics. And when I think back to David Donahoe and what he said today, building on his comments, we stand at the confluence of the classical, the math first, the theoretical, the academic. And now it's intersecting with the upstart, the data first, the empirical, the industrial. And this academic industrial confluence is exemplified in quantitative investing. The seeds for quantitative investing are sown in academia. And it's our privilege to unite these communities. It really is. And on behalf of me and my Wells Fargo teammates, I want to thank our distinguished speakers. Boy, you all just allowed us to view so many things in a different lens today, and you did a fantastic job. Thank you so much. I want to thank our partners at Temple, in particular, Dean Ron Anderson for all of your support, and most notably Edo Arialdi, who did yeoman's work in putting this together. So again, per Edo, please continue to visit the website. The publications from all of our participating faculty are listed there. In addition to that, the content was so good we didn't have time for question and answers. There is a website, there's an email address on the website. If you have questions, please continue to send them. We will forward them on to our faculty members here, because so many the catalyst for new research usually is born in practice. So by all means, please send your questions to us. And last, I'd say, hopefully the world's back to normal this time next year, and we hope to see you all on the Temple campus. Edo's got a really nice spot picked out for us, and Wells Fargo is delighted to be partnering with them, and we will see you all in Philly next year. Thank you so much.